Okay, can you guys hear me?
Yeah.
Okay. Test 1, 2. All right. Okay, so today I want to talk about capacitors. I kind of the last minute sent out an email with some documents on it, so hopefully you got a chance to print those out. If you didn't, it's fine. I'll put the stuff on the board. You can just kind of jot some things down. But at some point, you do want to print those documents out if you have the ability to print. If you don't, just take a look at them. It'll kind of drive home some of the points I want to talk about today. This is actually one of my favorite topics to talk about in the class, these devices that store energy. I want to talk about two types of devices that store energy. The first one is a capacitor. We'll start off talking about that, and then we'll talk about the inductor. We probably will not get to the inductor today. As a matter of fact, I know we won't get to the inductor today, but we'll go through some calculations, some theory about the capacitor, and then we'll move to the inductor, and then we'll keep going. So let me first start by saying, up until now, the only device we've talked about that you can connect to a battery is a resistor. Resistors do two things. I can use a resistor to divide voltage. I can use a resistor to limit current. And you know from lab that there are many, many, many different types of resistors. We talked about a fixed resistor. You learn how to color code a fixed resistor. We did an experiment where we looked at thermal resistors, we looked at photoresistors. There's many, many, many different types of resistors. You know, you can take a resistor in the form of a rheostat and change it to connect it as a potentiometer and vice versa. So this device called a capacitor, though, what it will do is give us the ability to store energy. Now, why would you want to store energy? And the answer is, why would you want to store anything? The reason you store something is to use it at a time. With this device called a capacitor, you can do exactly that. We can store energy. We can use that energy at a later time. You'll find out that this device called a capacitor has many, 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 many applications. So we'll get into the lecture. So I want to talk about, first of all, the term capacitor refers to a device that stores energy. We'll talk about capacitors, we'll talk about inductors. Both devices store energy. The main difference is, other than physical difference, is where they store the energy. For capacitors, capacitors store energy. Capacitors store energy in the electric field that exists between the plates of the capacitor. Now, you'll remember from a previous lecture that if I want to create voltage, all I got to do is separate charge. If I want to make voltage, I take charge and I separate it. So if I have a region of charge here and a region of charge here, say this is plus charge and this is minus charge, between that region of charge exists an electric field. So by separating this charge, doing work to separate this charge, I get what's called an electrical potential difference, or voltage. And between the two regions of the positive and negative charge, I get an electric field, an E field. Basically, what voltage is electrical potential energy. So anytime I have a separation of charge, I have potential energy. And that's exactly how we store energy in a capacitor. A capacitor, which basically is more than two conductors separated by an insulator, and we charge the plates, we charge the conductors. We charge one conductor to be positive, one to be negative, and in that way we store energy, potential energy, specifically electrical potential energy. So when you think of a capacitor, think of a device that stores energy, but the way we store the energy is by storing charge. We separate charge on the plates of the capacitor. So even though we understand that storing energy, I'll refer to a capacitor as a device to store charge. So think of it as a device to store charge. I want to start by talking about the way you can construct a capacitor. And they're pretty simple to make. As I said before, a capacitor is nothing more than two conductors separated by an insulator. So I'm going to draw what we call a parallel plate capacitor. Parallel plate, CAP. You'll see the word CAP, that's short for capacitor. For a parallel plate capacitor, what you do is you have, let's say, a plate of metal, that's a conductor. You have another plate, metal, conductor. And in between those two conductors, you have an insulator. So I'll draw the insulator like this. So this is the insulator. Now, when we talk about capacitors, they use the term dielectric. Dielectric. But that's just another word for an insulator. So you take a conductor, you take an insulator, you take another conductor, and I had a student say they call this an insulator sandwich. That's a good way to think about this. An insulator sandwich where the top and bottom piece is the bread. Those are two conductors. In between where you have the meat or the cheese, that would be the dielectric. So you can actually take, and I've done this, I've taken a piece of aluminum and another piece of aluminum, and I use glass. I took actually a mayonnaise jar, and I wrapped the outside of the mayonnaise jar with aluminum. I lined the inside of the mayonnaise jar with aluminum. You do it in a way where they don't touch each other. And you take two electrodes and connect to the aluminum on the inside and aluminum on the outside of the jar, and basically you have a capacitor, and will actually charge up and hold the charge. Now, it doesn't do it very well, but it does work. So, strictly speaking, a capacitor, two conductors separated by an insulator, and that insulator is called a dielectric. Now, the ability of the capacitor to store the charge. The ability to hold or store charge is called capacitance. Capacitor, the ability to store charge, capacitance. And we measure capacitance in a unit called a farad. A farad. That's actually named after a scientist. I don't know much about farad, but a farad, and a farad is a huge unit. So you hardly ever see farads. I know one of the students, one of you guys had some supercapacitors that you showed me, and there was like 100 farads or something. I'd never seen that before until the student showed me that. But typically, you'll see microfarads or picofarads. Those are common capacitor size. Most of them will probably be micro, but you'll see micro and pico. You'll see most of these, unless you get one of those supercapacitors. They will practically all be microfarads or picofarads. So a farad is actually a huge unit of capacitance. I want to show you an equation that kind of relates the physical properties of the capacitor. So I want to give you this equation. So if you're taking notes, go ahead and write this down. And I have the topic sheet that I emailed you, or I put it up on Blackboard, and I actually have all this in handouts for you. So you can jot it down, but it is in handouts, but you might want to make some notes with this. So let me give you this equation, and I'll come back to this picture, and we'll start understanding how this thing works by first looking at this equation. So the equation, C equals K A over D. So if I have my parallel plate capacitor, and then I have my dielectric, now usually what they would do, they would take these and kind of stack them together and literally make like a sandwich. They'll stack them together and they'll roll it up and they'll put it into some kind of a container, small. They have many different types of capacitors. First of all, let me say that. But they have the kind that you've probably seen in class. They look like a little cylinder. We'll actually roll this up and then connect leads to it. And on the handout that I gave you on Blackboard, when you look at that, you'll see where they actually have a film capacitor like that. You can actually see how it's constructed. They show you some metal foil and some kind of dielectric. But referring to this equation, the C is, of course, capacitance. The D, that's the distance between plates. So D in this diagram is the distance between the plates. So D would be like this distance from here to here. That's the distance between the plates. This A, that's the area of one plate. The area of one of the plates. Now in this parallel plate capacitor, we'll assume that the areas are the same. A would be like the area of one plate. So this area here, I'll shade it in. That's A. And then K has to do with the material you put in between the two conductors. So this is called the dielectric. So K is called the dielectric constant. Now, strictly speaking, that's incorrect, because there's actually another there's a constant we multiply by here, which I don't have handy, but it doesn't really matter because I lump it into this dielectric constant. Now, let's talk about how these relate to each other. How do they relate to each other? Well, you can clearly see that C and A are directly related. So C is directly related to A. C is directly related to A. Now that's actually kind of important to understand, because understanding how these variables relate to each other is going to help you to understand why the capacitor behaves the way it does, and I'll get to that here shortly. So you want to remember that the capacitance is directly proportional to the area of the plate. The more area I have, the more charge the capacitor can hold, and that should make sense to you. If I have more room, I can put more stuff on the plate of the capacitor. If I double the area, I can get twice as many particles, since charge, actual physical charge, you can think of as the presence of either positively charged particles or negatively charged particles. You can think of it like that. So C is directly related to A. The more area, the more capacitance. The lower the area, the smaller the capacitance. C is inversely related to D. Now that's kind of interesting. The bigger I make the distance between the plates, the bigger the distance between plates, the smaller the capacitance. Now, the way you can kind of wrap your mind around that is this. Remember, what is between the plates is electric field. So there's actually electric field between the plates of the capacitor. If I charge the top plate to be positive and the bottom plate to be negative, and when you charge it up, there's electric field that actually goes from the top plate to the bottom plate like that. Now, what do you know about fields? We've talked about basically three types of fields. We talked about gravitational fields, we talked about magnetic fields, and we talked about electric fields. And all fields kind of behave the same way in that if I think about magnets, if I have two magnets, say a north pole and a south pole, the closer they are together, the more you can feel the force of attraction or repulsion, depending on which way you have it turned. But if this is a north and this is a south, the closer they are, the more you can feel the force of attraction. The further they are apart, the less influence one magnet will have on the other. Well, electric fields work the same way. If the electric field has something to do with this device's ability to store charge, then the farther apart I have these plates, the weaker the field. That's going to affect the ability to store charge. That's going to affect the capacitance. So what you want to remember is the bigger the distance between the plates, the smaller the capacitance. And then the third thing, dielectric. So this dielectric material is some kind of insulator. It could be glass. There's many types of dielectric. I might have emailed you a table of dielectrics. If I didn't, when I post this stuff to Blackboard with the video, I'll make sure I include that. But what you'll see there is a table. Ideally you can have a vacuum, and then from there you can have a vacuum. You can have air, and then it goes up from there. Of course, a vacuum is an insulator. Dry air is a pretty good insulator, and then it goes up from there. So I'll give you a table of dielectric constants. You don't have to do anything with it. It's just that when you look at it, you'll see that I might have a dielectric that starts at less than 1 and go up to 7,500 or 10,000, depending on what material I have. So I can literally have a capacitor with a certain capacitance. I can take out one dielectric and put in another, and I can get either more or less capacitance, because capacitance also depends on this thing called the dielectric constant. So there's a direct proportionality between C and A. Sometimes I explain how with the dielectric, you can actually increase the capacitance. And sometimes I go into the physics of it. Sometimes I don't. It just depends on how much time I have. But right now, I won't go into the details of that. If we have time, I can talk about the dielectric constant a little bit later on. Or if somebody has particular interest in why it is that when I change from one dielectric to another, I can either increase or decrease the capacitance, let me know, and I'll be happy to go into the details of it. But for right now, these two right here will suffice. If you remember, C is directly proportional to A. The bigger the plates, the more room I have to charge. And inversely proportional to D. The further apart the plates, the less the capacitance I have, and that has to do with the strength of the magnetic field. Okay. So I said a lot here, so hopefully that's clear. This equation, you want to remember it, but I won't have you do much with this, because actually this is more of a physics thing. There's another equation that we're going to use that relates, I call it the Ohm's law for capacitors. You know, it relates values that you actually use to calculate to do problems in like a circuit, capacitor circuit. So I'll get to that here in a second. So let me get rid of this. I want to move on to a new discussion unless somebody has any question on anything I've talked about so far on the board. Anybody have any questions? Okay. So I actually want to use these relationships to help us understand how capacitors behave when you hook them up, like you hook resistors in series, or you can hook up resistors up in parallel, and you get a certain behavior from the resistors. Let's see how capacitors behave, and more importantly, let's understand why they behave the way they do. Now, before we do that, let me give you, I don't think I showed you the symbol for a capacitor. The capacitor symbol is like this. Capacitor symbol, and you'll see variations of that. You'll see this. So this is a variable capacitor. And then you'll see different variations of this. Now sometimes I will draw the capacitor like this. When I draw the parallel plate capacitor, I'll draw it like this. I really mean this. But sometimes I'll go real fast and I'll draw it like this. I think back in the old days, a long time ago, they used to use something called a condenser, but it's just another name for capacitor. And the symbol was actually this one. And somewhere along the line, they changed from this to this. So sometimes I'll draw this just because it looks close to the parallel plate capacitor. I just erased from the board. But realize the symbol is this. Now, every once in a while, you'll see a plus sign here. Maybe a plus and the minus sign here. This represents a polarized capacitor. A device that's polarized, what that means is It matters which end you hook up to the positive supply and which end you hook up to the negative supply. So if you see a positive sign right here or a positive and negative sign right across the symbol, that means that that capacitor is polarized. If you put it in backwards, you can actually cause the capacitor to explode. So if I have a polarized, now you guys are using multi-sim, so you really don't get a chance to do this. But at some point, when we get back together, if you take AC, you'll actually use these devices. And if you apply DC voltage to this and you get it reversed, you can actually cause this thing it'll pop like a firecracker. The bigger the capacitor, the bigger the pop. So, yeah, polarized capacitor. So if you don't see these on here, that means your capacitor is not polarized. Now here's what I want to show you. Let's review something that you already know for resistors. Really, really simple concept. You know that if I have two resistors in parallel, if I got R1 and R2 and in parallel, and I say, all right, find the total resistance. You'll say, well, that's easy. I can use, well, since I only have two, I can say R total. I can use a product over the sum rule. I can say R1 times R2 over R1 plus R2. Or I can say 1 over RT. Now we use REQ in class. I'm just using RT here because I'm going to use the T for the capacitors. I can use the reciprocal rule. 1 over RT is 1 over R1 plus 1 over R2. And I can keep doing that. We only have two resistors here, so this will suffice. But with that, I can have any number of resistors in parallel. And you can calculate this and get the total resistance. And you also know that when I have resistors in parallel, that total that you get using one of these equations is always smaller than the smallest resistor in the parallel connection. We get that. Well, when we talk about capacitors, it's the opposite. Now, what I mean by the opposite is this. I'll say it, and you write it down. I'll keep saying this just to emphasize it. Capacitors in parallel act like resistors in series. Capacitors in parallel act like resistors in series. I want you to write that down, but there's something else I want you to write down. So I'm out for a second to give you a second to write it down. I'm going to say something else, and I want you to write that down. So what I said was capacitors in parallel act like resistors in series. And the second thing is, what's true for resistors and current is true for capacitors and charge. So write that down. What's true for capacitors, I said that wrong. What's true for resistors and current? What's true for resistors and current is true for capacitor and charge. What's true for resistors and current is true for capacitors and charge. And I'll explain what that means here in a minute. So let me explain what I meant when I said capacitors in parallel act like resistors in series. Well, if I have two capacitors in parallel, let me put it over here. Say I have capacitors like this, two capacitors. And I'm going to use this symbol for the, even though I'm going to use these two symbols. So let's say I got these capacitors like this. I got C1 and C2. If I hook these up in parallel, you might think that I would use an equation like this to solve this, but it's actually the opposite. You would treat these as if they were resistors in series. If I have resistors in series, the way I would find the total resistance, I would add them. Well, here, the way I would find the total capacitance is I would add them. The total capacitance is C1 plus C2. So this top one, if this one was 3 microfarads, this was 6 microfarads, my total would be 3 plus 6. My total would be 9 microfarads. That's why I said capacitors in parallel act like resistors in series. If I have a series connection of resistors, the more resistors I put in series, the bigger the resistance. But if I have capacitors in parallel, the more capacitors I put in parallel, the bigger the capacitance. Adding more capacitors in parallel increases the capacitance, whereas if I add more resistors in parallel, it decreases the resistance. They're opposites. So you want to remember that capacitors in parallel act like resistors in series. Now, the question is why? Why is it that when I keep adding capacitors, instead of behaving like resistors, when I keep adding capacitors in parallel, instead of going down like resistors, the capacitance actually goes up? And to understand that, we got to go back to this relationship right here. Let's go back and look at this and think about it. Instead of drawing the capacitors like this, let me draw the actual plates. And then you'll see why this is true. If I have C1 and C2 now drawn, I'm not going to draw the dielectric between them. I'm just going to draw the plate. So here's one plate, and here is another plate. Here's a second capacitor plate, and there's the other plate. So this is C1, this is capacitor 2. And just for the purposes of this example, we're going to assume that they're exactly the same. The area here and the area here are the same. So what you've done is you've taken the capacitor and the second capacitor, and when you take that wire to connect the top leads together so you get a parallel connection, when you connect the wire from here to here, electrically what you've done, you've taken this conductor, this piece of metal, and through the wire, you've connected it to that second piece of metal. It's exactly like taking those two plates and pushing them together. Physically, it looks like this, but to the charge, electrically, it looks like you took that first plate and bumped it up against the second plate. And if the area here and the area here are the same, basically you've doubled the area. If you double the area, you're going to double the capacitance. If I make the area at all any bigger, I'm going to make the capacitance bigger. This is the reason why capacitors in parallel act like resistors in series. If I want to get more capacitance, I just add more capacitors in parallel. What you're doing electrically through these wires that connect one plate to the other, you're increasing the area. You're increasing the area. So you want to remember that capacitors in parallel act like resistors in series in that they're additive. They're additive. Okay, well, that's not too bad. If that's the case, then let's look at the other way to connect. What if instead of having my resistors in parallel, what if I have my resistors in series? Now what happens? If I have my resistors in series, R1 and R2, and I say, all right, find the total resistance. You're going to tell me that RT for this circuit is R1 plus R2. If I have resistors in series, the way I get the total resistance is just by adding them up. Well, capacitors in parallel act like resistors in series. Capacitors in series act like resistors in parallel. Capacitors in series act like resistors in parallel. So, if I had two capacitors instead of resistors in series, I got this. Again, I have 3 microfarads, 6 microfarads. I got C1 and C2. Now, capacitors in series act like resistors in parallel. So if I have resistors in parallel, what I would have is what I had before. The total would be R1 R2 over R1 plus R2. Well, capacitors in series act like resistors in parallel. So to find the total capacitance, I'm just going to change all my R's to C's. The total capacitance for this series circuit will be C1 times C2 over C1 plus C2. And just like resistors, you know, when I have resistors in parallel, the total resistance is always less than the smallest parallel resistor. Well, that's true for capacitors in series. If I have capacitors in series, the total capacitance is always less than the smallest capacitance in the series circuit. So for this one, the total capacitance has to be less than 3. Matter of fact, if you do the math, you'll find out that the total capacitance here will be 2 microfarads, which is less than 3, so it checks out. So capacitors in series act like resistors in parallel, and any resistor formula that we use, like this one, all you got to do is change the R's to C's, and you got the right capacitor equation. So what I'm saying is, you know, you can use 1 over RT is equal to 1 over R2 plus 1 over R3. Well, since that's true for resistors, if I want the correct formula for capacitors in series, all I got to do is get rid of the R's and make them T's. So this would be, when I said T's, I meant C's. This would be CT, this would be C1, this would be C2, and so forth. Just keep going on and on and on and on. So capacitors in series act like resistors in parallel. The more capacitors I have in series, the smaller the capacitance. Now you should wonder, okay, well, I get that, but why? Why is it that if I keep adding capacitors to this, the total capacitance goes down? Why? To understand that, let's go back to my drawing of parallel plate capacitors. So what I'm going to do is take 3 capacitors and I'm going to connect them up in series. So I'm going to have like capacitors like this. I'm going to have C1, C2, and C3 in series, but I don't want to draw it like that. I'm going to exaggerate that bottom part. I'm going to draw the parallel plate so it looks more like a parallel plate capacitor. So what I'm going to do is this. I'm going to draw C1 as a parallel plate capacitor. Here's C2, and here's C3. So I got C1, C2, I got C3. I'm going to connect these in series by putting a jumper here, here, and now I got the 3 capacitors in series. And what I'm going to do is I'm going to charge these capacitors up. How do you charge a capacitor up? All you do is hook it to a voltage source. Imagine I hook this to a voltage source. When I hook it to a voltage source, current is going to flow into the capacitors, and it's going to charge those capacitors up. Remember, current is just charge per unit time. That's what we looked at the second week of class. Current is charge per unit time, coulombs per second. So I'm going to charge these capacitors up for a certain amount of time, and I'll get a certain amount of charge in that time. Now here is where you have to think about this the right way. Remember when I said what's true for resistors and current is true for charge and capacitors. What's true for resistors and current is true for charge and capacitors. I want to explain what I mean by that. If I have resistors in series, R1 and R2. If I tell you how much current is flowing into this network, if I tell you the amount of current flowing into that connection, you would know the current everywhere in the circuit, because you know in the series circuit, current is the same everywhere. In a series circuit, current is the same everywhere. What's true for current and resistors is true for charge and capacitance. What I'm saying is, once you charge this up, the charge is the same everywhere if I have them connected up in series. Over here, the current is the same everywhere. Here, the charge will be the same everywhere. So whatever charge C1 had, C2 and C3 will have the same charge because it's the current that deposits the charge on the plates. It's just the current is the same everywhere. You would expect the charge to be the same everywhere. So what I'm going to do is draw the charge capacitor. Now, when the capacitor charges up, the way to think about it is one plate gets charged positively, and the other plate gets charged negatively like that. So I'm going to draw positive charge on one plate and negative charge on the other plate. Now I'm showing just three charges, but you know there's many more, trillions of charges. I'm just drawing it this way. My point is that since the current is the same everywhere, since this is a series circuit, the current is the same everywhere, the charge is going to be the same on each of these capacitors. So if I'm drawing 3 here, I got to show 3 here. It's plus, and 3 here, that's minus. And then 3 here, that's plus, and then 3 here, that's minus. So once I do that, these capacitors charge up, you take a snapshot of it, that's what it looks like. Now, does anybody notice anything interesting about the diagram I just drew? Anything stand out to anybody? If you do, you can open your mics and just yell at me. Anything that you notice about this diagram right here that's interesting? Well, I'll tell you what. What'd you say? Go ahead.
Looks like a battery cell.
It does look like a battery. Matter of fact, you can think of a capacitor as a short-term battery. I often wondered when I first studied capacitors back a long time ago, why would you need a capacitor and a battery? Because basically a capacitor, once you charge it up, looks like a battery. A battery separates charge. A capacitor holds charge that has been separated. And in both cases, you have an electrical potential difference. You got a voltage. The difference is, though, there's 2 big differences between a capacitor and a regular. Number one, you can charge a capacitor way faster than you can charge a battery. You can charge a capacitor, well, I'll show you here, you can charge them. You actually have control over how fast you can charge a capacitor. That's one difference between a capacitor and a battery, is the speed at which you can charge a capacitor. The second thing is the amount of current you can get from a capacitor. The amount of current you can get from a battery is determined. We talked about some of the properties like the maximum current rating and voltage. There's a lot for a battery, but with a capacitor, you can get what's called a surge current. So you can get a huge amount of current from a capacitor. There's no way you can get from a battery. Now, what I'm going to do is at some point, probably next time we do the video, I'll give you a sheet. We actually look at some of these properties. You look at how much current you can get from a capacitor, and I'll show you one example that'll blow your mind. We're going to put in milliamps into the capacitor and get out amps, get out a huge amount of current. And then when we talk about magnetism, there's a device that will, if I have time, we'll talk about something called a rail gun. I don't know if you ever heard of a rail gun, but I'll show you how a rail gun is constructed and how it works. But this rail gun, you can fire it with a capacitor. And if you use a capacitor instead of a battery, you'll get a lot more punch out of this thing called a rail gun. Don't worry about what it is right now, but it gets really interesting. I think you'll enjoy it. So yeah, this does look like a battery. But let me give you a hint though. Look in between. I'm going to circle this, the inside, the guts of this thing. Anybody notice anything in that circle? Or it's not a circle, but what do you notice inside of that shape I drew? It should be very obvious. I mean, it might be so simple you're not seeing it. But anybody knows anything particularly interesting inside that circle? I guess Kevin must not be out there because Kevin always answers, even if it's a guest. So Kevin must not be out there today. Well, let me help you out. What happens if you count the number of plus and minus charges in the circle? What do you notice?
They're the same.
Kevin is out there. Kevin holding back on me. Kevin says they're the same. You see it? I have the same number of positive and negative charges in the circle. Not only that, look, I connect these two capacitors were separate until I connected them in series. Once I connect these in series, once I do this, I have negative and positive charge in equal amounts, and I have a way for them to get together. Remember, like charges repel, but unlike charges attract. So the negative charge on the plate of the top capacitor is going to be attracted to the positive charge on the bottom capacitor. It's exactly the same amount of charge, one positive, one negative, and I provided a way for them to get together. So basically what's going to happen, these are going to get together and cancel out, and these are going to get together and cancel out. And what's going to happen is the charge inside this whole circle is going to cancel out. It's going to give zero. For every positive I have a negative, and all the charge in between those two plates are canceled out. And this is kind of hard to think about, but what you've done is electrically, not physically, but electrically, you've increased the distance. By doing what I just showed you with that plus and minus charge, it's exactly like taking the plates and moving them further apart. And you can see here, if I increase the distance between the plates, well, the capacitance is going to drop off like that because they're inversely related. This is why if I keep adding capacitors in series, the capacitance is going to go down, 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 because electrically what you're doing is you're increasing the D. You're increasing it, and the more of those you have in series, the less capacitors you can expect to get. So you want to remember, capacitors in series act like resistors in parallel, capacitors in parallel act like resistors in series. And let me go ahead and put the formulas on the board, and then I'm going to give you another formula. Now, I don't know if that's in any book anywhere. I probably got that out of one of my physics books or something. So make sure you get this, write this down, because I don't know if you'll see that again. I don't think it's in your book. But let me give you the formulas, and then I want to work a problem. And I don't know if I brought my problem. I'll find it. I got a book here, but I want to get a problem that we can work. Now that homework, I put homework 1, capacitor homework 1 out on your email, and I'll put it on it's on Blackboard now. So I want to work one of those homework problems because we get to use these principles we just learned.
Excuse me, sir.
Yes, sir.
I see the homework, but I don't know how I'm gonna do to print that.
You can write it on a piece of paper. You don't have to print it. If you don't have a printer, just write it out on your hand. Write it out in your hand. Yeah, you don't have to print it. Let me write these equations down.
About the graph.
About the what?
About the graph. The graph.
The graph?
Yep.
What about it?
I don't know how to print that because I know we're gonna use that.
Yeah, you don't have to. Well, it doesn't really matter because all your exams are going to be done at home. So if you need that graph for an exam, which you might, you can just bring it up on your computer. You don't have to print it out. I don't know how you guys are. I'm old school, and you guys are used to doing stuff on your phone. I just like to have paper in my hand. I don't like doing stuff on a screen. I don't like reading the screen or writing. I don't like any of that. I want it in my hand. So if you can just open it up on a screen, that's fine. You don't have to print it out. Now, something that you're going to send to me, if you're going to turn it in, then you're going to have to do the picture thing like you did in your lab. Take a picture, turn it to a PDF, and send it to me. But for what we're doing, just take a look at it. I'm actually going to draw that, so you don't have to worry about printing it out. It's just kind of nice if you have a handy, you can look at it as I'm talking about it, because their picture is going to be way better than mine. So that shouldn't be a problem. Now, let me write these formulas down, and then I'm going to give you one more formula that's important, and then we're going to work a problem. And I probably should put it over here. So for capacitors in parallel, we learned that the total capacitance We just add them up. This is parallel. If they're in series, we use parallel resistor equations. Basically, we just change the R's to C's. So if they're in series, CT, if there's two of them, will be C1 by C2, C1 plus C2. We can use 1 over CT equals 1 over C1 is 1 over C2, and they'll keep adding up like that. So we looked at this for series, and then this for parallel. Well, there's one more equation that turns out to be pretty important, and that's this one. C equals Q on V. Now, I call this a question.
Yeah, I got a question for you.
Uh-huh.
With your resistance and capacitance 1 over formulas, why do you keep writing 1 over RCT equals 1 over whatever plus 1 over whatever instead of 1 over?
You mean this one?
Yeah.
Why do
Like-
I keep writing this?
Yeah, so instead of saying 1 over RT equals 1 over R2 plus whatever, why not just say take out the 1 over the RT and say 1 over R1 plus 1 over R2?
So he's saying RT equals 1 over 1 over R1
Yeah.
plus 1 over R2. Yeah, and that's
Isn't
actually what. Go ahead.
Isn't that the actual formula?
It is the actual formula. Does anybody know why I write it this way? That's actually a good question. A very good question. So that is the actual formula. If you want to work it out, you stick that in your calculator and bam, you got it. But why do I write it this way? What's the point of that? Why do I write it this way? What is this actually? Anybody know? What is 1 over R? You remember 1 over R because we talked about it in the experiment, the Ohm's law experiment. 1 over R is actually what?
Conductance.
Conductance, G, right? So normally, if you look at your book, I haven't really looked at your book, but what they'll do in parallel, I don't know if you can see if I write this low. I hope you can see down here. But this is actually GT plus G1 plus G2. A lot of books, when they show parallel circuits, they don't even talk about resistance, they talk about conductance. And that's what this is. This is really the conductance. So to add all this up and get the total conductance, so if you add all the conductances up, you get the total conductance, and then you would stick that into this. RT is 1 over G. Most books do it that way. So instead of talking about it in terms of conductance, I just use it as, I just leave the conductance in terms of resistance so you can kind of see where things come from. But you're totally fine doing it this way because when you actually want to solve this equation, that's what you're doing. But the way I showed you to solve on your calculator using the inverse X key, the reciprocal key, it's pretty easy to put it in this way. You just put it in that way, bam, hit the reciprocal. I say reciprocate. Hit the reciprocal key and you can get it real fast. So either way, it's all right. I don't care how you think about it. But that's the reason why I write it the way I do, because I'm really thinking of this in terms of conductance. And most books, when they introduce parallel circuits, they'll show you this conductance thing. It looks more like resistors in series. So in parallels, conductances kind of act like the series formula for resistors. So they'll write it that way. So that's a really, really good question. Anybody else have any other questions? What time are we done? What? Oh, we got plenty of time. I'm thinking it's 1:50, but it's 2:20. So if there's no more questions, let me go to this. I call this the Ohm's law I'm calling it the Ohm's law for capacitors. If you look that up, you won't see it written this way. I'm saying it's like, for capacitors, this is the capacitor's Ohm's law. So let me get rid of this stuff. And you can see what this does for us. This gives us capacitance in terms of things that we've already known or we've talked about. This, of course, is capacitance. It's in farads. This is voltage. The unit will be volts. Does anybody remember what Q is? What is Q?
Charge.
Judge.
Q is charge. So Q is charge. And the unit for charge, if you forgot, is the coulomb, a capital C. Now don't confuse this C with this C. So Q has units, the brackets mean units of coulombs. But if that C, if it's written before the equal sign, then that's capacitance. So this is the one we'll use to solve problems. Now what I want to do is, make sure you have this written down. And again, if you have that thing on Blackboard printed out or you got it open up on your screen, you got this. I don't give you this. I think you got to write this stuff down. But this I give you. This is on that sheet. Now what I want to do is, from that homework 1, if you look at that homework 1, capacitor homework 1, the very first problem, I want to work that. Because by working that, you got to use this stuff. So I want to look at this. And then I want to explain how you would do the other problems that are not as simple as the one that we're going to do today as an example. So if you got that sheet, take it out. If not, look online, download it. You can open it up on your computer. I'm going to copy the circuit on the board, but anybody have that sheet handy? Anybody have it? Capacitor homework 1, does anybody have it? What I need is the page number off the bottom of the page. If you got that printout, there should be a page number on the bottom. That'll just save me a little time. Anybody have it?
It's 218.
Okay, thank you. All right. So if you don't have it, don't worry about it. I'm gonna put the circuit on the board, and we're gonna work it together. But you make sure you have pen and paper because I want you to work it with me. So let me get it on the board. All right, this is 80 volts. Oops, 80 volts, not 8 volts. And that's VT. And then we got C1, C2, C3. And this is 0.02 microfarads. And this is 0.05. And this is 0.1. Okay, so given this problem, what they want you to do, they want you to find, now if these are resistors, what you would do, you would find the total current, you would find the voltage drop. Here, we're not going to find the total current, capacitor is charge. So here we're going to find the total charge and then each voltage drop. So how would we approach a problem like this? And the way you do it is pretty simple. All you got to do is change in your mind, change these to resistors and say, all right, if I had all resistors hooked up, how are the capacitors are hooked up? If I have 3 resistors in series, what would I do? What you would do if I have resistors in series, the very first thing you would do is you find the total resistance. And then you would use that to find the total current. And then you would use the current in Ohm's law to find the voltage drop across each resistor. Well, you do exactly the same thing here. With capacitors, you're going to find the total capacitance. You'll use that to find the total, not current, because remember, with resistors is current, with capacitors is charge. So we'll find the total capacitance, and we'll find the total charge, and then we'll use these two to get a voltage across each capacitor. So it's exactly the same way. If you ever get confused or you get lost on what to do with capacitors, just change it to resistors, and however you would approach that problem is how you would approach this one. The idea is if you have a more complex circuit, which we'll give you here, we'll get to in just a second. If I had like resistors in a series parallel circuit, remember how we did it in class? We started from the side of the circuit that was furthest away from the voltage source, and we start combining stuff, either in series or parallel. We keep combining and redrawing the circuit until I get to one simple series circuit, and then I work backwards and use that series circuit to help solve the rest of the other problems. That's exactly what we'll do here with the capacitors. So I'll find the total capacitance, I'll find the total charge, and then I'll find the voltage drop across each capacitor using C equals Q on V. If I have resistors to get V, it would be I times R. For capacitors, I would solve this for V and use this to get the voltage drops across each capacitor. So I want to be quiet for a minute. I want you to think about how you would start to solve this. What would you do to get CT? What would you do to get QT? And then use that QT to give you the voltages across each capacitor. I'm going to be quiet for a couple minutes. If you have pen and paper, go ahead and start to work this out a little bit. And then we'll get back and we'll do them together.
Excuse me, sir.
Yes, sir.
I don't see anything down the whiteboard,
You
up
don't
the
see anything?
down board. I'm not seeing anything up the whiteboard.
You can't see the whiteboard?
The white, I don't see C equal
You can't see the equation up there.
up the
See,
blackboard.
The equation's in the glare.
Yeah,
The
yeah.
white-
I think C equals Q uh, up V, I think. Something like that.
You can't. You say the equation is not clear?
Yeah, he said that
The
it's
equation,
not clear. It's not clear.
the equation C equals Q over V is in the glare, so nobody can see it. That's
This
the
one?
problem. Yes, that one.
That's in the glare? Wow. I got to with this lighting. I should turn the camera around so you guys can see what I'm working with. I don't know how to get this lighting any better. So it's C equals Q on V. Okay, so go ahead and try to work with this. I'm going to run to my other computer. I think I got logged on here so I can see what you guys are seeing. I want to see how my lighting is. Go ahead and work that for a second. And I will. I'll be right back. We'll see if we can. I want to see what you guys are seeing. I can see the glare on my other computer, so maybe I'm gonna try to do something with this place. Let's go ahead and look at this though. So what do I want to do first here? What would I do first to get CT? What would I do? I'm going to erase this to make some room, but how would I approach this? Anybody?
Find the total capacitance.
And the way I do that, remember, capacitors in series act like resistors in parallel. So I'm going to use the 1/C formula. Now, somebody mentioned before that to find the total capacitance, you're going to do 1/C1 plus 1/, you're going to do that. But if you use a reciprocal key, then I'm going to write it out the way I always write it out. And you can just use a reciprocal key and get the answer real quick if you remember how I showed you to use it. So this, if I write right here, can you see? Make sure you can see. So 1/CT is 1/C1 is 0.02. Now I'm not going to put the microfarads down there. I'll just put the whole numbers, and they know the answer will be in microfarads if I do it this way. So this is 1/0.5 plus 1/0.1. So you hit this plus your reciprocal key plus this and your reciprocal key plus this and your reciprocal key. We'll add it up, hit your reciprocal key one last time, and automatically it'll give you CT. Anybody tell me what CT is?
$0.00588.
Now, I don't remember that being an answer. Is that 1/C or is that CT?
That's CT.
Yeah, try it again.
I got 0.0125.
And I think that's the answer. The only reason I remember is because I just did this problem in another class. So whoever that was that got this, redo that. 0.02, 0.05, 0.1, and make sure that this is right. Anybody second this number? Do I have more than 2 people doing it?
Yeah.
Okay. So my total capacitance, now the way to think about it is, if you put all these together into one, and what you have is one big giant capacitor, and this capacitance would be 0.0125 microfarads. So now, once I get that, that will be equivalent to finding the total resistance if I have resistors instead of capacitors. Well, what would you do next? If I have resistors, once I get the total resistance, I would use that to find the total current. I would say that the total current is V over the total resistance that you found. Well, here we're going to find the total charge. Here's what I'm going to use the equation: C equals Q on V, because what I want is the total charge. If I have the total capacitance, if I use that total voltage, then that'll give me the total charge, which is what I want. So go ahead and do that. Let's find the total charge. Huh?
I got 1.
Okay, so you put 80 here.
Yep.
Here we put 0.0125. Now, that's not right. This would be 0.0125. Now, this is microfarads. I'm going to leave that as microfarads. And if you solve that for Q, somebody said you got 1. So you do it, you get 1, but since this is in micro, it'll actually be 1 microfarad. So somebody verified that you get 1 microfarad. Did you get 1 microfarad for that? Anybody else get 1 microfarad?
What's the unit there? It's not farad, is it?
Microfarad. This is see what you're saying. Thank you. Who was that? That was, don't tell me. Who was that? It wasn't Steve. Yeah, I can't think. I know who it is.
I have a much younger voice than Steve.
It's Jacob. It's Jacob, right?
Yeah.
Yeah, he's right. He got me. It was a micro. Should be microcoulombs. Q is microcoulombs. Now, remember, charge for capacitors is like current for resistors. So since this is a series circuit, if this were resistors and you found the total, if you found the charge anywhere, I said that wrong. If these were resistors, you found the current anywhere, you found the current everywhere. The current is the same everywhere in the series circuit with resistors. Well, here, charge is like current. If I find the charge anywhere, I found the charge everywhere. So by saying that Q is 1 microcoulomb, what you really mean is this capacitor has 1 microcoulomb. I'm just going to draw it like that. This capacitor gets 1 microcoulomb, and this capacitor gets 1 microcoulomb. That's the reason earlier I said that charge for capacitors is like current for resistors. If you think about it that way, it'll help you solve the problem. By finding the charge here, you found the charge for every capacitor. So now all you got to do is find the voltage across each capacitor. And you know how to do that. You're going to go to that, what I call Ohm's law for capacitors. C equals Q on V for each individual capacitor. And that's going to give you what we're looking for. So you go ahead and do that. I'm going to write it out neatly so you can see what I'm saying. So, I don't know where the glare is. C equals Q on V. So V is going to equal Q on C. So if I want V1, it's going to be Q. I want to subscript that because it's the same everywhere. On C1, V2 is Q on C2. And V3 is Q on C3. Those are the equations we use to solve for each individual voltage across each capacitor. So put your numbers in there, calculate, and then you should be good to go. So all the Q's are the same. It's all going to be 1 microcoulomb. But this is 0.02. Now notice I got microcoulomb and microfarad. If you leave this as microcoulomb and microfarad, then that's going to cross out. So I can just take 1 divided by 0.02. That's kind of nice. So I got 1 microcoulomb on and then 1 microcoulomb on 0.1. All right. So this should do it for us. So let's finish this up. What do you get when you divide 1 by 0.02?
50.
You get 50 volts. So right away over here, take your coloring pen. You still use your coloring pens and pencils. You get 50 volts across this capacitor. What do you get when you divide 1 by 0.05?
20.
You get 20. So right away, 20 volts across this capacitor. Now, if you wanted to, you can do this the same way. You can say, well, you do, if you get 1 divided by 0.1, or remember Kirchhoff's voltage law? Kirchhoff's voltage law always applies. I don't care if you have resistors, capacitors, it doesn't matter. Whatever you have, the voltage drops have to add up to the total. So if this is 50, this is 20, if I have a total of 80, this has to be what?
10.
10.
It's got to be 10. Kirchhoff's voltage law has to be valid. And now this is solved. I found all my charges. I got my voltages. I'm good to go. Okay? Now, if you have that homework sheet, look at problem number, oh, by the way, on the homework sheet that I gave you a second page of solutions. If you look, I think I emailed it to you. If I didn't, I will. But you should have a page, the odd number problems. I give you solutions to so you can see if you're doing them that way. Now, when I grade this, I'm going to just pick one, probably the hardest one on here. I'm going to just pick one of them. And if you get everything right except for the one I picked, you're going to get 0 on it. So make sure you take your time, go through it, and work it out. Check with other people if you want to make sure you turn in a perfect paper. So what I want you to do is look at problem number 8, figure 15.8 on that homework sheet. Now, I'm not going to draw it, but I'm going to show you, if you don't have it in front of you, here's what they did. They took another capacitor on that next homework problem, and they put it right here. They put the other capacitor right here like this. Now let's say I gave you this. Get rid of this stuff. What if I gave you a problem like this? Now you don't need to know the values. I just want to know how you would solve this. What would you do if I gave you? Well, I did give it to you on that homework sheet. So how are you going to solve a problem like this? I gave you this. I put another capacitor here, and maybe another one right here. What would you do for this problem? This is C1, this is C2, this is C3, and this is C4. What would you do for something like this? How would you approach this
I
problem?
think we're gonna do.
Huh? This is C3. What would you do? If these were
I think we're gonna do this. I
Go
think we're
ahead.
gonna do the same thing like the resistor. We take the first C2 and C3.
Exactly. You take C2 and C3, and you're going to redraw it like that. Now, what I like to do is put nodes up here, because it's easier to keep track of, plus when other people look at it that don't know what you're doing, you just seem smart when you do it like this. So if your wives or girlfriends or boyfriends or whoever are looking at it, you do this, it just makes you seem a little smarter. It looks more technical. But what you can do then is, you correctly said, we're going to combine these. Now remember, when I combine, when I combine them, I'm going to get an equivalent circuit. I don't know if I'm in the glare or not, but C1 is still here. C4 is still there. I don't know how I'm drawing my capacitor. So C4 is still there. But these two are in parallel. Remember, capacitors in parallel, you add them. So whatever this is, you add them up. This would be C2 plus C3 for that value. And then you got the same problem we just got through doing. The same one. So for every problem, some of these, like when you get down to number 9, that's the hard one on here. I got this worked out too. I got the solution to number 9, so I worked it out for you. I'll wait to see if you can do it, and then I'll give it to you, the solution if you want it. But on number 9 is exactly the same way. Your goal is to reduce everything down to a series circuit, just like resistors. So whoever said that, you treat it just like a resistor circuit. You're exactly right. The only thing is, remember, what's true for resistors and current is true for charge and capacitors. And also remember that capacitors in parallel act like resistors in series and vice versa. So if you keep that in mind, then all these problems should be a piece of cake. Should be pretty easy to do. Well, we got a few minutes left, but I think that's all I want to do with this stuff. When we get back together, it gets really, really, really interesting. I think you guys are going to like this capacitor stuff. What we're going to do next time is look at, what we've done here is we looked at capacitors that were already charged up. They're already charged up. Well, there's three different times, T-I-M-E. There's 3 different times we can look at a capacitor circuit. Let me just show you that, and then I'll end the video. I hope I pushed the record button. Did I push the record button? I think it's recording. Let me show you this real quick. So there's 3 different times that we can look at a circuit, and depending on when we look at it, you'll get different results. The first time is, I call T sub 0. So right here, that's the time. This is the time right before cap gets current. So that's one time. The second time is, I don't know what to call it. The second time is when cap is charging. So you got this. This is a time. I can look at it. Let's say I have a capacitor circuit. I'll show you real quick. So let's say I have a simple capacitor circuit like this, where I have a switch, I got a resistor, and I got a capacitor. I close the switch. Right before the capacitor starts to charge up, that's this first time. It behaves a certain way. Then while it's charging up, that's the second time. It behaves a different way. And eventually, let's say this is a 10-volt battery, eventually that capacitor is going to charge up to 10 volts. So when it's fully charged, that's the third time. And each one of these times, depending on when you look at it, the circuit it behaves a different way. So we get back together on, we got to wait till Friday for this. When we get back together on Friday, we're going to go through this, and this is where this gets kind of interesting. It also gets a little bit more mathy if that's a word. So make sure you just follow what I'm doing. If you want to read about this in the book or look at it on YouTube, you can. But it gets kind of cool. I think you guys will enjoy this. Now, for lab, I don't even know if I signed the lab. You guys should be doing. Let me see what I signed you before. You turned in the multi-sim lab, and the next one you should have did was on circuits. But I don't think I put up a formal link for that. I don't know if I did or I didn't. I gotta check. But we're gonna do it. I have all the labs printed out in order. If you don't have a book, so the next one after the multi-sim lab, the one that you just basically duplicated what I did. The next one will be one out of your book on the series circuits. You'll build that in multi-sim and just show me all the values, just like you did on the first sheet. The next one, I think it might be the parallel lab, but I'll put up a formal link on Blackboard. So you can keep going and doing these labs. We're going to finish out the labs in multi-sim. We won't get together and do any physical labs. So, we don't have any other way to do it because of this virus situation. Well, I'm out of time. Does anybody have any questions for me before I sign off?
Yes, I got a question.
Okay.
I got a question about the summer semester.
The summer semester.
We're going to take online. We're going to take online or in class?
That's a very good question. So, as of right now, here's what I was told. I'm not 100% sure it's going to be online, but I got an email from my chair. Actually, I got a phone call. They told us to go ahead and prepare the courses, assume they're going to be online. So we're going to go ahead and prepare like we're going to be online, but if something happens, we'll actually do face-to-face. So right now, I'm making the assumption that we'll do it online. So understand that they'll probably be online, not 100% sure, but they'll probably be online, and they're also going to be the summer semester for our class is going to be 10 weeks. So if you're going to sign up for summer, consider that. Looking at something that'll very, very possibly be online, and then the time will be shorter. The total time for the semester will be shorter, which means each individual class will be longer. So we'll have to see how that works out. Now, as soon as I hear something about that, if I find out they're not going to be online, I'll let you guys know. As I hear stuff, I'll let you know. But I think I had a phone call Friday. Yeah, Friday I had a phone call Thursday or Friday from the department chair, and he told me to go ahead and prepare the classes if I was going to teach summer online. So that's what I'm thinking. It's going to be online. Of course, at the last minute, things can turn around. They can say, hey, we're going to do face-to-face, or maybe they'll do part of it online and then move the last part of the semester face-to-face if things start to clean up with the virus situation. But as of right now, I was told to prepare the classes as if I was going to present it online. So I'm going to assume they're going to be online. Anybody else have a question? Okay, if you do, you got my number. You can go ahead and send me a text. I think that's all I want to say. Just look out for Wednesday. I'll put up some kind of formal thing for your lab, so you'll know what's going on for lab. And then this video, I'll make it available sometime between tonight and tomorrow. If you missed this or you want to watch it again, it'll be up on YouTube, and you can link it through Blackboard. So you guys have a great rest of the day. Please stay safe, and I will see you or talk to you on Friday.